Right, today we're going to go through how to do integration involving harder fractions such as these. Because we can't straight away use our standard integrals such as log or inverse tan, we must firstly split these fractions up into simpler individual fractions. So there's a couple of things we must note before we actually begin. The numerator must have a lower degree than the denominator, otherwise we're going to have to do long division. And also, the denominator must be factorized. So in our first example, we've got x plus 1 over 2x squared plus x. Now, we can simplify that into x plus 1 over x times 2x plus 1 and write that as two different fractions with unknown constants a and b in the numerators. Now, in order to find these constants, we're going to equate what the numerators would look like if we were to combine these two fractions together. So it will be a times 2x plus 1 and b times x. And all of that is supposed to be equals to x plus 1. We could, of course, try to equate the coefficients of x and the coefficients of the constant. But a much better way is to actually make good substitutions of x in order to eliminate one of the unknown variables and find the other one. In this case, we'll choose x equals to 0, which will get rid of b, so that we have 0 plus 1 equals to a times 0 plus 1 plus 0, which gives us a equals to 1. Now that we know what a is, we can let x equals to 1 and substitute all that in to get 2 equals to, since a is 1, 1 times 2 plus 1 plus b, which tells us that b is minus 1. Now that we know what a and b are, we can change this integral into an integration of two much simpler fractions, remembering that a was 1, so we have 1 over x minus, from above, minus 1 over 2x plus 1. Now both of these will be log, so we have ln x minus a half ln 2x plus 1 plus c, and optionally you can combine these into a single log. In this next example, we want to integrate 10 over x minus 1 times x squared plus 9 dx. Now, when we split this fraction up, we are doing something new here. We have a over x minus 1, just like before, but because x squared plus 9 is a quadratic, our denominator is x squared plus 9, and our numerator should be a linear function, so we're going to call it bx plus c. Now, if you ever see a cubic denominator, such as this, then your numerator would be bx squared, plus cx plus d. The reason we do this is that if we just use a single constant on top of these higher powers in the denominator, we're not going to be able to find the correct coefficients. So now equating 10 with what we'll get if we do a times x squared plus 9 and bx plus c times x minus 1, we want to find a, b, and c. So again, we're going to use a good substitution of x, such as x equals to 1, which tells us that 10 equals to a times 1 plus 9 plus, that's all gone, so it's 0, which means that a equals to 1. Since we know a equals to 1, we can substitute x equals to 0 to eliminate the b and help us find c, which means when x equals to 0, 10 equals to 9a, that's gone, so we have minus c, which means 10 equals to 9 minus c, since a is 1, which tells us that c equals to negative 1. If we continue with that, we have x, let's try x equals to 2, since that seems to be an easy number to use as well. 10 equals to a times 4 plus 9 plus 2b plus c times 1. Now, we already found what a and c are, so we can substitute those in. here we have 13 plus 2b minus 1, which tells us that b is also negative 1. So now that we go back to our integral, and since we found that a equals to 1, b equals to minus 1, and c equals to minus 1, we put all that back into our split up fraction, which gives us integral of 1 over x minus 1 minus x plus 1 over x squared plus 9 dx. Now the first part simply is ln x minus 1, and the following part we've split this fraction into 2 bits. We have the integral of x over x squared plus 9, and we have the integral of 1 over x squared plus 9. Now the first part is going to be a half ln x squared plus 9, and the other part is going to be a third inverse tan of x plus x over 3. Now finally we can combine these two ln's together. Again, that's optional, so we have ln x minus 1 over square root of x squared plus 9 minus a third inverse tan of x over 3 plus c. In our final example, we want to integrate x squared over x plus 1 times x plus 2 dx. Now the first thing we notice is that x squared is degree 2 and our denominator is also degree 2, which means that we can't carry out the partial fraction process. We must first do long division. Now it's a little inconvenient that we must have to expand this before we do long division, but let's do that. So we want to divide x squared by that product, so it's x squared plus 3x plus 2. Carry out the long division. We have x squared plus 3x plus 2, which we minus, so we have minus 3x minus 2 as our remainder, which means that this integral can be turned into 1 minus 3x plus 2 over x plus 1 x plus 2 dx. Now again, here is where we want to split this up into individual fractions. So we have a over x plus 1 and b over x plus 2. Now, again, equating that with 3x plus 2, a times x plus 2. People call this cross multiply, but cross multiply is only when we have equations. This is simply combining fractions. Just make sure you know that distinction. And b times x plus 1. So we know that 3x plus 2 must equals to all this. Now, here we can make convenient substitutions of x, which will be x equals to minus 1 to get rid of the b, which tells us that minus 3 plus 2 equals to a times minus 1 plus 2 plus 0. So we have minus 1 equals to a. Also, we can use x equals to minus 2 to ignore the a, which gives us minus 6 plus 2 equals to 0 plus b times minus 2 plus 1, which is minus 1. So we have minus 4 equals to minus b, which means b equals to 4. Right. Now that we know what a and b are, we go back to our integral, and we want to find 1 minus a over, well, a is 1, minus 1, sorry, over x plus 1. And we also have, just make sure we have brackets there, plus 4 over x plus 2 dx. Now carefully going through all the negative signs, we have this turning out to be x, minus minus becomes plus, so x plus ln, x plus 1, and minus plus becomes minus, so we have minus 4 ln x plus 2 plus c. Now that should be enough examples for us to actually try some questions involving harder fractions. However, this method does not always apply. For example, if we have the integral of 1 over x squared plus 2x plus 5, this is a positive definite quadratic, which means that we cannot factorize this, and we'll have to use a slightly different method to do this. Now this is different to what we did today, but just quickly going through that, we need to complete the square in the denominator. So we have bracket x plus 1 all squared plus 4 dx, which turns out that this is an inverse tan. Let's see.